Good day to Dr. Lai and fellow lecturers. My name is Kathirevan, Thamil Chelevan, metric number 230-63795/1. Today's topic of discussion will be on the medical device pulse oximeter and the first order circuit involved. So let's start with the introduction. So what is pulse oximeter? Well, pulse oximetry is the non-invasive measurement of oxygen saturation. So how does the pulse oximeter work? The oximeter emits light through the skin and measures the amount of oxygen in the blood. The measurement is based on the detection of hemoglobin and deoxyhemoglobin. Two different light wavelengths are used to measure the actual difference in the absorption spectra of HbO2 and Hb. Deoxygenated hemoglobin has absorption at 660 nanometers and uses red LED light to generate that wavelength of light. On the other hand, oxygenated hemoglobin has an absorption at 940 nanometers and uses infrared LED to generate that wavelength of light. Samples cannot be taken at the same time because there is only one photodetector for two signals, therefore signals must be multiplexed. Now, let's discuss the circuit theory used in the oximeter. In this device, the first order circuit is applied as a filter. For filtration to happen, current needs to be converted into a voltage. In this current to voltage converter, the feedback resistor and capacitor is an integral part for filtering purposes. Conversion is performed using a current to voltage converter which consists of a single supply, low input offset voltage, low input offset and bias current TRIAMP embedded in the K53 together with a feedback resistance and a capacitor for filtering purposes. This circuit combines a current voltage to a voltage converter and a low pass filter to improve the signal treatment. The output voltage and the cut frequency are given by these formulas. Equation 1, voltage out equals to photosensor cathode current times by the first resistance. Equation 2, Fc is equals to 1 over 2 pi in parentheses R1 times by C1 equals to 125 Hz. A 125 Hz low pass filter is to remove high frequency noise from the received signal. Here we can see the current to voltage converter circuit diagram. Now let's look at the filter circuit diagram inside this oximeter. In this block, there are 4 passive filters and an active filter. This is the active filter. Filter 1 is a low-pass filter with a cutoff frequency of 6 Hz. Its function is to eliminate high-frequency noise. This is the equation of the filter cut frequency, F0 equals to 1 over 2 pi RC. The second filter is a notch filter. It serves to remove the 60 Hz line interference. This is the diagram of the notch filter. There are 3 capacitors and 3 resistors. The notch filter is referenced to VCC over 2 to add an offset voltage. The notch filter cutoff frequency and design parameters are represented by these equations. F0 equals to 1 over 2 pi R1 C1. R1 equals to R2 equals to 2R3. And C1 equals to C2 equals to C3 over 2. Moving on to filter 3. Filter 3 is a high-pass filter, in which a high-pass filter means that it passes signals with a frequency higher than the cutoff frequency and attenuates signal with frequencies lower than the cutoff frequency. The capacitor will remove the DC, this capacitor here. Next, the fourth filter is the first order active 6 Hz low pass filter that provides a gain of 31. This is the diagram of the first order active 6 Hz low pass filter. It consists of 1 capacitor and 2 resistors. This filter uses a K53 internal op-amp to be developed because it has high input impedance, low output impedance and the voltage gain of 31 determined by the resistor network within the feedback loop. These are the equations used to determine the filter cutoff frequency and gain. F0 equals to 1 over R2 C1 and A equals to negative R2 over R1. Now let's have a look at the frequency response curve. The frequency response curve of this filter is using a simulation software. So here we have the pass band. Here we have the corner frequency, Fc, and here is the slope. The last filter is a 4.8 Hz low pass filter, similar to the first one, represented by this equation, F0 equals to 1 over 2 pi RC. Now, let's have some additional information. This right here is a VREF generator circuit, as well as the diagram shown. This voltage reference component allows to provide stable precision reference voltage for the analog resources such as the biopotential in this oximeter design. Thank you so much for watching. Thank you to Dr. Lai and fellow lecturers for watching this YouTube video from me. Thank you.